we will first start from recalling that, remembering that from where we started. So what is our goal in this course? So our goal is to learn chaos. So learn chaos. So then what is the definition? So definition of the chaos is means if any system, means as we know the orbits, what does orbit means? So if any system's orbits follow these three property. One is this sensitive dependence of initial condition. Second is transitivity, and third is a dense set of periodic points. So we will to see that whether a system has a chaos or not. So theoretically we can check these three things. If a system orbit contains these three property, we will say that the system has chaos. Now how far we have gone? So we have up to now we know what does orbit means, what is the definition of orbit. So we have to learn something like the another things like stability. What does stability means of a fixed point? Then we can talk about the sensitive dependence of the initial conditions. So and then we have to define the transitivity. What does the transitivity means? So we have to define what does the sensitive dependence means, and we how far we reach. We know that there is an initial condition and how the initial condition will go in the iteration of any map. Transitivity, we have to define the transitivity. So this we don't know a little bit. And third thing is we know only in the third part we know only what does the periodic point means. We have to know that how theoretically we can say that a system has periodic orbits. We know that what is meant by the periodic orbits or periodic points, but we don't know which system has the periodic point and that periodic point is stable or not. That we have to know. So for that we are going to know in next few classes the stability of a periodic point. And then we have to define what does the dense set of a dense set means. What does a dense set means? So that is the basically things that in the previous class we planned that in the beginning of this class we will see what does the famous word the butterfly effect means. So butterfly effect butterfly effect means the sensitive dependence of the initial condition. So this is the butterfly effect. So this is the butterfly effect. So this is butterfly effect is the fancy term of this sensitive dependence of the initial condition. So how does this butterfly effect came into the picture? So this term is coined by Lorentz. So once I am putting his exact statement. So he once state that this question, does the flap of a butterfly flap of butterfly's wing in Brazil set of a tornado in Texas. So this statement was posed by famous chaos who because of whom we know the chaos, what the chaos. So this is Lawrence. So Lawrence posed these questions, and from this question, because you see that here flap of a butterfly wings means small change of the initial conditions, small change in the condition. So if can small change of condition create a big thing in the far away positions, that means that system is, whether the system has a sensitive dependence of the initial condition or not. So that basically means the butterfly effect does not mean anything other than the sensitive dependence of the initial condition. Now that is the thing. So now we will go back, because if you want to know, you want to learn what does this actually mean in terms of mathematics, we have to know so many things. So first of all, first and foremost, the thing is that we have to know what does what does the stability of a system means. So up to now we know what does a fixed point means, but we don't know what is the stability of a fixed point. So that's how we are going towards, by cobweb map we are going towards that whether the system has a stability or not. So that was that. So is it clear, Subhusaji? So what does the butterfly effect means? We will go it in a further, we will go it in the elaboration, much more elaborative things, but I want to just introduce that this is the thing. Okay. Oh, okay. So then let's go back to our previous schedule, that previous thing, that what where was we, that we learned that what is called the linear map, how we can define a linear map, and how the what is the fixed point of the linear map. So for any linear map, the only possible fixed point is the origin. That means x equal to 0 and y equal to 0. This point is fixed point. Now by the applying the cobweb map, we are trying to see that whether any initial condition are going toward this origin or it is diverging from the origin. So we have seen that if this slope or this constant a is in between 0 to 1, then if you start from any initial condition, the system will evolve and it will approach towards the fixed point, that is 0 0. So that means this fixed point has a approaching toward the fixed point. And if a become greater than and I have asked you to do for the cobweb for a greater than 1 and a is between 0 to 1. Have you done this that thing? You will check that what is the behavior. Okay. Yeah. You will. Okay, no problem. So let me just save the result, that in this case you will find that the initial condition similar to this condition, but it is spiral out. So it is not kind like that. It is rounding around the fixed point and going away from the fixed point. Here you will see for a greater than 1, it will also away from the origin. So that's the thing, that you will see that away from origin, wherever initial condition you will start, you will see that the finally the system will away from the origin, and in this case you will see that system will spiral in, means just opposite to this case. If you start from x2, it will slowly move like this, and it will finally go toward origin. So for this case you will find that go towards origin spirally. So that is the two thing that you will find. So from the cobweb diagram, geometrically we can see that two things. Basically geometrically we can see two things. One is that if modulus of A, the magnitude of A if is greater than 1, then the systems will always goes away from the fixed point. So it's from the cobweb diagram, and if modulus of A is less than 1, so if you see here, so if it is modulus of A is less than 1, and here in these two cases you will see that the system will always converge to the fixed point, and in these two cases where the modulus of A is larger than 1, the both will go further away from the origin. So for A less than A, so then you will find that converges to the origin, and here the origin is the fixed point. So that's all. Now let us prove that thing. So you see whether why the proof is required. So it is very important. Why, if we can tell from this cobweb diagram, so why the mathematical proof is needed? So you see from cobweb diagram you will get a feeling. So to prove that you have to check for every initial condition. We only saw for only one initial condition the behavior of the system for only one initial condition x0. But can we from the cobweb diagram in general we can say something for the system? So the answer is no. So to that we have to prove the theorem. So you have to prove the theorem that for A greater than 0, the system will always go further from fixed point, and for modulus of A is less than 1, then it is always origin. So and the proof is very simple, you see. So where you see that its orbit orbit will be x0, x1, x2, x3, xn, and so far so on. Now what will be the x0? X0 is the initial condition. What will be the x1? X1 will be f of x0, and what is f? It is ax, so ax0. What will be x2? F of x1, that is a of x1, and a of x1, if I put the value of x1 here, what will get? A into a of x0, so that basically a square x0. Now for f3 similarly we will get a cube x0, and for an we will get a to the power n x0. Now you see, if modulus of A is less than 1, then this series, that say suppose for given example, suppose A is half, then what will be the A? Half. What will be the A square? That is 1/4. What will be the A cube? That is 1/8. What will be the A fourth? That will be 1/2. So 1/8, 16, 132. So this way 164. Now you see that if this is the case, then A is greater than A square, is greater than A cube, is greater than A to the power 4, is greater than A to the power 5, and that means that this is a decreasing series, and this will be decreasing and decreasing. So for A less than 0, A less than 1, the sequence of A square, A cube, A4, An is a decreasing, that is called the monotonically decreasing series. And where it will go? So from this series we can safely say that. And if in terms of mathematics, I don't want to go to the nitty-gritty of those mathematical things, that the limit, and from the limit you can actually prove that this sequence, if A less than 1, then this sequence has a limit, that limit is actually 0. So that means, this means that A to the power n, if limit n tends to infinity, this will approach to 0. So if I infinitely multiply half, I will actually get 0. This basically say that. So from that we can say that, so then from here we can say that limit n tends to infinity a to the power n into x, x0, so that will tends to 0 because x0 is a constant, and so if I multiply x0 in both sides, so 0 multiplied by 0 is 0, so basically a to the power n x0 will go to 0. So then this means n tends to infinity. And what do you know, what does xn means? Xn means a to the power n x0, so that is basically means xn tends to 0. That means if I infinitely iterate the system from x0, I will finally approach towards the 0. So that is the theorem basically says. So theorem says that if a is less than 0, the system will converge to the origin. So that means if I infinitely iterate the system through the map f, I will slowly converge to the 0. So the both as theorem says. So this is theorem. This is a general for every map, every linear map. If a is less than 0, then we can, without using of anything, we can say that the system's fate will be that it will go to origin. And in the other case, if a greater than 0, if a greater than, suppose, and for this is the first case, so this is the first case where a is less than 0, so this is the first case, case 1, and this is the second case, case 2. If suppose mod a is greater than 1, then what will be the sequence? The sequence will remain same. And for a greater than 0, if you suppose say a number 2, so 2, then 4, then 8, means a is 2, a square is 4, a cube is 8, a 4 is 16. So you can see this is a, then this will become a increasing, monotonically increasing series. And from the limit, from the definition of the limit, you can actually prove that the limit n tends to infinity, an will tends towards infinity. Now if we multiply x0 both sides, so infinity multiplied by x0 will remain infinity. So that means you can write it this way, limit n tends to infinity, x0 a to the power n will tends to infinity, will tends to infinity. Now this means the limit n tends to infinity, x n will go towards infinity. So this means if my a is greater than 1, value of the a is greater than 1, the system will always diverge from the origin and it will go towards infinity. So that's how the thing is. So if without drawing any cobweb, now we can say if my linear maps value of that constant a is greater than 1, it is means its magnitude. So if it is greater than 1, the system is not stable, system will not come towards the origin, it will go farther away from the origin, and it will eventually, if I infinitely iterate through our map, the system eventually will go towards infinity. And if modulus of a is less than 1, then the system will eventually come towards the fixed point, and we can say that the fixed point is stable in this case. In this case, for the first case where it is a less than 1, we can say it is a stable fixed point. Stable fixed point, that means x0 equal to 0 is stable. Here we can say that x0 equal to 0 is unstable. So that's the thing. Now Sobhusaji, did you get that? Now we will, means whatever we, means it is basically a very simple thing, but if you have any question you can ask me, or otherwise I will go to the thing that is very interesting thing. Okay. Okay. So then let's go towards that thing. Okay. So as I mentioned, let me give me a moment. Okay. So now we will see that another thing which is called the affine map. So affine map. So previously what we have seen the linear map. So linear map, if I go to here, then okay, here if I go to here, then you can see linear map means if I put x equal to 0, y equal to become 0. Now for the affine map it is not the case. So for the affine map, the affine map will is actually, the affine map looks like, okay, y equal to ax plus b. Now you see, if I put x equal to 0, y will become b. So y does not become 0. So that makes it the name the affine map. So basically it is called the affine map. That's how it is defined. Now let's see why we are interested in the affine map, or through the affine map how far we can go. So how what is the usefulness of the affine map? So let's first draw the map here, or maybe I will draw it later. So where this affine map will come? So I can go in the mathematical way, or I would love to go in other way, in application way. So let's see an example. So from that example it will be very clear. So one example is, so how mammals regulate their body temperature. So that is the thing. So we'll see naturally this affine map will come into the picture if I want to study the regulation of the body temperature of mammals. Well, as you know that the mammals who can regulate their body temperature according to their environment, and the body temperature remain quite fixed because they can regulate. That's why it remains fixed. So through this we will see that. So to see the map, we all study a little bit of physics in 12th. So I guess you know this law. So this is called the Newton's cooling law. It's called Newton's cooling law. It basically says that if some system is there whose temperature is T, suppose there is some system whose temperature is T, and at that moment the environment temperature, suppose environment temperature is T environment. Suppose in your hand something is there, suppose in your hand some metallic thing is there, that metallic temperature of the metal is suppose T, and at that time the temperature of the surrounding of the metal, that means the temperature of the environment, is T environment. Now in case of mammals also you can think like that, the temperature of body temperature of the mammals is T, capital T, and in where that mammal lives, the environment temperature is T environment. Then Newton's cooling laws says that it follows that the temperature of the mammals Tt, so how does it change with time? So here small t means time. So it says this is minus small k into T minus T environment. So that's it. Now this says that the rate of change of the body temperature T of a mammal with time. So these basically, as we have previously from previous lecture, we know that what is the meanings of the dt. It basically means in time duration dt, the change in the mammal's body temperature is, suppose when t goes to t to t plus dt, then temperature t goes to t from t plus dt. Now the rate of, what is the rate of change? Rate of change is basically dt by small dt. So that is there. Now suppose thing like that we measure, means we are actually constantly monitoring that animal and we are taking its body temperature after every minute. So here dt is 1 minute. After every minute I am checking its body temperature. So suppose that at nth time its body temperature was Tn plus 1, and in the previous instance its body temperature, previous minute, suppose in 11th minute its body temperature was something Tn plus 1, T11, and in the 10th minute, in the previous minute, its body temperature is Tn. It should, according to the Newton's law, it should be equal to, since dt equal to 1, it should be equal to minus k into the body temperature of the previous moment, that means Tn minus T environment. And we are assuming that the environment temperature is remain constant throughout. Assumption is environment temperature is remain constant. Okay, that's assumption. So let's deduce the map from here. So Tn plus 1 is basically minus k Tn plus Tn. And Subhusaji, if you feel free to ask question. If you did not get anything, so stop me there and ask me. Okay. 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 K stands for, means it is a constant. It basically says that what is the radiation rates. Means it's basically it's a physics term, but you can think like that, how efficient in the heat transfer, means the heat from that animal's body, how in what rate it is actually going from the animal's body to environment. So basically that stands that's captured with this constant K. Means it is. Yeah, it is. There is a name. It's called, I think it is called, means I forget the exact name, but its name maybe in Newton's cooling law you will get that thing. So maybe I think its name is. It's actually. I mean, it's basically depend on the heat capacity. So it's actually heat capacity. It's called heat capacity. You can see like that. It's heat capacity. So it is actually heat capacity. So how much heat will radiate per unit gradient of the temperature and unit time. It is called heat capacity. But then Tn plus T, and then what is the, then there is K T environment. So this is basically Tn 1 minus Kn and plus K T environment. So you will see that this is a map. This is a map. Why this is a map? So in the map we know that the n plus 1th iteration, here we can say in this mathematical language that n plus 1th iteration can be derived from this nth iteration. So you can think like that. So suppose that, now let us suppose that here this is not there, n is not there. So suppose that this is a constant A and this is a constant B. So you can write it like this: Tn plus 1 is A Tn plus B. Now you can write it in this way, that Tn plus 1 can be written as a function of that in the n plus 1th temperature can be written as a function of the nth temperature. This is a map. Okay. this is a map, so we can write it in this way. This is a map, and you see this is the affine map. That's why we are interested in affine map, means there is a mathematical reason behind it. So because you will see in the next lecture that what is the mathematical reason behind it, but I find this is another way to introduce the affine map. So this is basically affine map. So this is this is a affine map. Now let us study. This is the thing. Now let us study whether a mammals, when a mammals can maintain its constant body temperature, when it can, in terms of cobweb. Let's see. So first, so there can be we will see the two cases. So one case is, so they are similar to the previous case, similar to the linear case, where a can takes value, a can takes four kinds of value, this and this. I will only show you these two kinds of behavior, and the third and fourth kinds of behavior are similar to 1 and 2, and I will ask you to do it by your own, and you will find the same thing. Okay, let's first see the now the question is this is the how that if you as regulator mammals, you will see that that's how its temperature is going with time. Now the question is, can that mammals maintain its body temperature or not? Body temperature or not? Let's see. And as let's first case. So for first case, if its constant a is greater than 1, then what will happen? Let's see. A greater than 1. So this is my x-axis. Suppose this is my x-axis, means here you can write it in this way, y equal to same fx. You can write also in this way. That doesn't matter what you write. Instead of t, you actually write x and y. That doesn't affect at all on the behavior. So this will be the, will write me tn. This is tn plus 1. Okay. Now this is my identical line. This is my, let's try this is my identical line. This identical line means, this is means y equal to x line, or tn plus 1 equal to tn line. I will use y equal to x for our convenience. X, this is y. Now first we will draw the linear map. Linear map means we will, if the B was not there, then what the maps, how the maps will look like. So map, if B was not there, how the map will look like? The map will be, so if, since A is greater than 1, so the map will be in this side, and it is it will start from origin, so it will look like this. So this is the graph, that y equal to ax. Now what we have, that at x equal to 0, the y equal to not 0 but b. So then suppose this is b, then since ax is same, so this will be parallel to this line, so this will look like this kind of, sorry, okay. And this, what this line is y equal to ax plus b. Okay, now let's cobweb diagram, and first see that what is the fixed point. So you'll see here the fixed point is, if you draw this line here further, and if you draw here, so you will see that the fixed point is here. This is the fixed point, this is the fixed point. Now the C is, now if we are observing and the mammals is like that. Suppose its body temperature somewhere here, suppose it's T0 or suppose it's X0. Now we will go to draw a cobweb diagram to see what is the fate of that animal. So first what we will do, first I will draw a vertical line that will cross the identical line here, and this point will be x0 x0. Then I will draw further line, vertical line. I will draw this line so I'll draw this line like that, where it will cut. It should be vertical. I am actually horrible with drawing straight line, so I'm trying as best I can do. So this will probably hit here. Okay, I don't know. Okay, so then that means this is my first iterate. This will be my first iterate. So this is actually x1 comma x0. This is my first iterate. So in x-axis, if I draw the first iterate, what it will go? It will go like here. It will go here. So this is my x1 first iterate. So you actually observe that if its a is greater than 1, then you will observe that its body temperature after next minute, means if you observe in 10 minutes, at 11 minutes its body temperature actually increases to x1. Now in the next minute this is x1, this is x1. So you will see that it will cut here somewhere and somewhere here, and this will continue to here. So you will see that it comes here x2. So you will see that for a greater than 1, its body temperature is continuously increasing. So what you, from the cobweb diagram, what actually you find? So let me draw it in the very small region, then it is be very helpful to see, actually pictorially see. So let's start from here. First here it goes here. Suppose my x0 is here, x0 from here to here, then it is goes here, exit, then it will hit here. This is actually x0 x1. This will be, sorry, this is x0 x1. This is x1. So this is my first iterate. This is my initial condition. This will be first iterate. This will be x1. Then from using a cobweb diagram, if I draw, you will see it will hit here, and it will be hit here. The x2 will be, this will be x2. So you see that the mammal's body temperature will increases from x0 to x1, x1 to x2, and it will increasing, it will be increasing further, and it will actually go towards infinity. So that is the thing. You will see that at previous moment it was 0, then it means not 0, means it is actually increasing. You will find that the body temperature actually mammals increasing, and it is not remain constant at all. So that is very bad for that animal. Means from that you can conclude that that animal will going to die, because that is very sad thing. But you have, means that the means a, that means a, if you find that a is greater than 1, that that will means that the heat regulation system of that mammals is not at all fine. That animal is not at all fine. Now let's see another limit, that if a is less than 1, can the can the animals survive and maintain its body temperature? Let's see that. Subhudaji, did you get that what I am saying? But means, have you got that idea? If express means no, in Newton's cooling law, means I am just showing you in this way, but it is proved that Newton's cooling law has been proved that if A is greater than 1, then that means the temperature of that things will increase with time. That is true. Now let's see if A is less than 1. If A is less than 1, so then let's first draw what is this is actually identical line y equal to x. Let's first draw if A less than 1, and linear map will look like this. So this will be, suppose, y equal to ax, and now if B is this, suppose B is this. Suppose B is this, then y equal to ax plus b will be parallel to this line. This will look like, yes, this is not quite parallel, but let's see, it's actually parallel. So this line is actually y equal to ax plus b, this is y equal to x. Now let's see, suppose if I starting from initial condition x0, suppose it is here, and here in this case this is the fixed point, this is the fixed point, since identical line and that map cross sects that intersect there, so that's why this is called the fixed point. So let's see where is first. We will draw this x0 point here, this is x0 point, and will up further away here. So this will be my x0 comma x1, then from here to I stray from here horizontally, then it will cut here, that is my x1, and from here we actually going to this direction, it will be x1 x2. Now Subhusaji, you see that my initial condition going towards this fixed point, now here to here, now here to here, here to here, and you see that it is going ultimately going towards the fixed point. So this means if you find that experimentally find that the mammal's body temperature, if mammal's heat regulation capability is such that that this constant, if you find that this constant is less than 1, you will find that the body temperature, if suppose this is a humans and it's here the 30, this is actually fixed point, means its constant body temperature, that is 37 degrees centigrade. Now suppose in winter it's a perfectly healthy human's body temperature get decreased by, see, in winter our body temperature fluctuates, and suppose that it decreased by some amount, some degree, then if that individual is healthy enough, then its body temperature will quickly go towards this 37 degrees centigrade if its A is less than 1. Now in another limit, if suppose in the contrary to the winter, if in summer its body temperature is little bit higher, if become little bit higher, then what it will become. So let rub this fixed point. So suppose if you start from here, so again from start, you'll see here. So this is my actually x1 comma x0, because this is the line, this is the first iterate. Now first iterate to I, if I want to x1 I have to go here. So this will become x1, this here to here, this will become x1, this is become x2 oh sorry, x1 x2. Now you see, it is, if I start from little bit higher than 37 degrees, suppose in summer, or if healthy individual's body temperature get little bit higher, it quickly return back toward the 37 degrees centigrade. So that's how 37 degrees centigrade. So that's how you can say that that individual is perfectly fine. If A is less than 1, that means that that mammals can regulate heats perfectly fine, and if its body temperature get little bit higher or little bit lower, it immediately go back to its previous temperature. In case of human, it is 37 degrees centigrade. So that is how, if A is less than 1, then you can say that the individuals, that mammals can regulate their, if A less than 1, that you can say that that mammal can regulate their mammals can regulate his or her body temperature. So is there any question, Sopusaji? So okay, yeah. Now that's the thing, means if you ask that whether we can treat a human in this way, so I can say that that is the difference between a physicist and physician. So for a physician like me, if some patient come to me, and if you want to know he is actually terribly ill or not, what I will do, by some experiment, I will find what is the constant, what is this constant, and if this constant become greater than 1, I will say that your body temperature is actually increasing with time. That means you got a fever and you are terribly ill. Your body actually are not capable of regulate the heat in a correct way, means in the way that that body ought to be, and you actually going to die sadly. A physicist will do so, and a physician will by putting a thermometer, and he will say that you have a fever. But since the physicist has this funny way to check whether a patient is terribly ill or not, so that's why a patient should always avoid a physicist and he should go to a physician. And if I find that A is less than 1, I can tell that your body temperature, the regulation system is perfectly fine, and you are a perfectly fine individual. So that's the main thing. So that's the joke. So if from jokes apart, in terms of mathematics, so this is called the fixed point. So in this case, if you find that the system will come to the fixed point, and the fixed point is stable here. For A less than 1, the fixed point is stable here, and for A greater than 1, the fixed point is not stable. And you see that what is the difference between this affine map and the linear map. So what is the basic difference between the affine map and this linear map? So in case of the linear map also, we have seen that where the theorem is. So this is the theorem. So we have seen that we have actually proved that for A greater than 1, it goes to infinity. And in the affine map, we have also find that if A greater than 1, the temperature goes to infinity. If A less than 1, it goes to origin, that means x equal to 0, to fixed point. Here also for A less than 1, it goes to fixed point. what only change the affine in the affine map is that fixed point is not this origin, rather than fixed point is has a value which is not equal to 0. So that is the only difference. So by some, if anyone can take this fixed point to the origin, it seems from the cobweb diagram that the affine map and the linear map will look same. So that is our next thing, that we will prove that yes, indeed is it true that if the magnitude of the A is greater than 1, and if the magnitude of the greater than 1, the fixed point will not be stable, the system will go to infinity, and if magnitude of A is less than 1, the system will go towards the fixed point. Let's prove that. So first let us calculate that fixed point. Suppose this is the fixed point, T star is the fixed point, and we know that what is the definition of the fixed point. So fixed point will remain fixed under the action of the map. And what is map here? Here the map is A T star plus B. So here the fixed point is T star 1 minus A equal to B. So T star will be B by 1 minus A. So this will be the fixed point. This is the actually fixed point. This is the fixed point. This is the fixed point. Now let's prove that theorem. So here you see that suppose Hn, what will be the Hn? Okay, or not Hn, it's Tn, the temperature. Tn is actually A Tn plus 1, actually A Tn plus B. Now since we want to, this is T star, so you want to take this fixed point to origin, but it has value. So if I subtract the every coordinate, every x coordinate by T star and y coordinate by T star, we will take it to the origin, because if I from x coordinate, if I subtract T star, it becomes 0. From y coordinate, if I subtract T star, it will become 0. So this point will become 0 0, and this map will look to the similar to the linear map. So we will do that thing. So Tn plus 1 minus T star equal to A Tn plus B minus T star. And we know from our definition, T star means A T star plus B. So we'll write that here, minus A T star minus B. So this means Tn plus 1 minus T star is actually A Tn minus T star, A Tn minus T star, only A Tn minus T star, because this B got cancelled here. Okay. Now if I put here, suppose T1 minus T star will be, how it will look like, T1 minus T star will be A T0 minus T star. What will be then T2 minus T star? That will be A T1 minus T star. So if I put T1 minus T star value from the previous expression, we'll get A square T0 minus T star. Now if I put T3 minus T star, I again will got A cube T0 minus T star. So here we'll get Tn minus T star will be An T0 minus T star. So that we will find. And now similar to the previous case, if A is modulus of A is greater than 1, then we know that the limit n tends to infinity, A to the power n will be tends to infinity. Now if we multiply by this, so limit n tends to infinity, An Tn minus T star will go to infinity. So this means that since this n goes to infinity, so this means limit n tends to infinity, this means An Tn, okay, this means that, okay, not Tn, okay, I forgot, this is not A Tn, this is T0, right, this is T0, if I multiply T0 by Tn star. So this means, and this means nothing but this is Tn minus, this is Tn minus T star. So Tn minus T star tends to infinity, and limit n tends to infinity Tn. Now since T star is a constant and it does not depend on the n, so it is a constant, and if I add T star both side, and infinity plus something will remain infinity, so that means infinity. You see that the temperature of that individual will actually go towards infinity. In theoretical sense infinity means, in practical sense it can't go to infinity, it will go somewhere, then that individual will die, and that the equation will change, because it can't, then we can't use the same equation. If that individual dies, we can't use the same equation as we have used before, that a dead individual's K will become different than the living beings. So that is, but theoretically if that individual remain alive, and if it's the constant A is remain same, then you will see that the body temperature theoretically will go to infinity. So that is the first thing, that if A greater than 1, for affine map also the fixed point is unstable and the temperature will go to infinity. Now in the other limit, let's see, in the other limit, that means if mod A is less than 1, where does it go? So mod A less than 1, then limit n tends to infinity. We know that A n tends to 0. Let multiply both side by that, n T n minus T star will tends to 0. 0 multiplied by anything remains 0, so we have no problem here. So limit n tends to infinity, and we know from our this expression, this is a to the power n, T0 minus T star is Tn minus T star. Oh, I again do a mistake, so this is T0, so this will be Tn minus T star goes to 0. Now you see limit n tends to infinity, Tn goes to T star. So that's how we can say that now if A less than 0, A less than 1, the affine, the fixed point is stable, and the system actually go towards this fixed point, the Tn. Eventually, if I iterate the system with the same map infinitely, it goes toward the fixed point T star. And in terms of our the things that we will say that the that is the thing, that system is stable. So that's the all. So we see that it doesn't matter whether it is affine or linear, it depends on the value of A. If A modulus of A is greater than 1, then the fixed point will become unstable and the system will go to infinity, and if the modulus A is less than 1, the system will stable and it go towards the fixed point. So that's all. Now if you have any question, you can ask me. Huh. Huh. Night and day. Huh. Right. Then we actually call it fever. Then we call it is we got fever. That's the thing. So I will suggest that if you got fever, you have had to see a doctor, not a physician, or a physician, not a physicist. So that's the thing. So thank you for joining. Okay. Okay, then Then in the next class we'll meet in the Monday. Okay, then I am ending this meeting. Yeah, yeah. I will touch upon that thing. The hormone means this is basically the same thing. I will just introduce the equation. You can do it with yourself. But in the next class, I want to want to introduce what does mean by the stability analysis, linear stability analysis in case of map.